Hello, this is Mrs. Ross, and this is 4.2 real zeros of a polynomial function. Let me give you a heads up. There's a whole lot of math-ese here. I'm going to skip over most of it because I would much rather do the thing. Like, what do I need to know to do the problems? I don't need to know the math theory. Okay, if you're really interested in math theory, we can go back through that. But I'm just trying to get you to apply whatever it is. So it talks about the zeros of a polynomial, make it zero. They're the x-intercepts, okay? Okay. This talks about how to find the roots. We're going to do some problems with that. So this has a quadratic, which has a degree of 2, and they factored it. Then it talks about multiplicity. So multiplicity is how many times a root is a zero, and we're going to talk about it. I'll show you. There's a way that you can figure it out, okay? Like, for example, here, all of these are roots. They all have a multiplicity of 1 since they are all different. Here, you have a root that is 3, but it has a multiplicity of 2 because it occurs 2 times. I'll show you here in a minute. So we are going to use this page. It says if the multiplicity of a 0 is odd, then it crosses the x-axis. If it's even, it touches the x-axis. Nope. Descartes' rule of signs. This is actually one that's better shown, okay? But these are the two things you would need to look at. So if f of x has a sign change, there will be a positive real 0. If f of negative x has a sign change, there will be one negative real 0. And we're going to work those out. Rational zero theorem. Yeah, this is gobbledygook until you actually do something with it. Hi, Lily. Hold. Okay, so we're going to talk about the rational zero theorem at a later time because this is all math gobbledygook. Oh boy, this is where it comes together. So this says factor the quadratic expression. Okay, so if I'm going to factor this expression, x squared, so I'm going to put x in front, and I have 2. 2 is a prime number, which is awesome because it's just going to be 2 and 1. And since this is negative, it goes in front of the larger number. Once you have this factored, we're going to set this equal to 0. That means one of these two factors is 0. So we have x minus 2 is equal to 0, and x plus 1 is equal to 0. And if we solve these for x, this should look super familiar. This goes away, my equals comes down. Okay, so this function has 2 zeros, x equals 2 and negative 1, and both zeros, that is not even an English word, zeros have a multiplicity of 1 because they both show up once. All right, so let's change the pen color here. And we did number 1, we're going to do number 2. Use the polynomial function whose factor form is this for the following questions. A says, what is the degree of the function? So I'm going to do that one up here. I know that this is going to result in x cubed. This is going to result in x squared. And this is going to result in x to the 1, which we normally don't write. But I'm going to add all of these exponents. And the degree of this function is 6. Okay. B says, what are the zeros of this function and what are their multiplicity? This is not fun, just so you know. So I know that this could be equal to 0, or this could be equal to 0, or this could be equal to 0. So I'm going to solve. Equals 2. I'm going to solve here. Solve here. Okay, so these are the zeros. the multiplicity is going to be the exponent. So the root that x equals 2 has a multiplicity of 3 because that's cubed. The root that x equals -3 has a multiplicity of 2 because it's squared. And then this last one is just x, so it has a multiplicity of 1. Okay, and I'm going to change colors because C is a little bit diabolical. So C says, for which zeros of the function will the graph cross or touch the x-axis at that point? So what we know from one of the crazy theorems that we already had is, it's the one that I told you guys that we're actually going to use. It's the identifying the multiplicity of, okay. Either case, if the multiplicity is odd, then it touches, no, it crosses, my bad. It crosses x-axis. If the multiplicity is even, then it touches the x-axis. Okay, so let's take a look at our multiplicities up here. At x is equal to 2, which has a multiplicity of 3, the graph will cross. Graph crosses at 2, 0. At x equals -3, the graph is going, which has a multiplicity of 2, the graph will touch at -3, 0. And then at, I don't even know if you guys can see this, x equals 5, 5, which has a multiplicity of 1, the graph crosses at 5, 0. Okay. All right, let's keep going. Using Descartes' rule of signs to determine the number of positive and negative real zeros for these functions. Oh, big sigh. Okay, so we're going to look at f of x as it is, and it looks like it changes signs once. So I know that f of x changes signs either from positive to negative or negative to positive once. So it has one positive real zero. Okay. The other thing that we have to do is we have to find f of negative x. So I'm going to plug negative x into every place there's x up here. And this is what I get. So I get negative x to the 5th plus 3x to the 4th plus 2x to the 3rd. That's a lie. Yeah, no, because it was negative and it becomes positive. Okay, sorry. Minus 7x squared minus 2. Okay, so I change signs twice. Okay, so f of negative x changes signs twice. So it has 2 or no negative real zeros. Okay, so delightful. I'm going to erase this and we'll do B. B, so let's see how many sign changes we have for f of x. We have no sign, so f of x has no sign changes. So it has no positive real roots. Okay, so now I need to find f of negative x. So f of negative x. So I'm going to plug negative x into here. So I get negative x to the 5th plus x to the 4th minus 4x cubed plus 3x minus x plus 1. All right, we got lots of sign changes here. So we got 1, 2, 3. So we have 3 sign changes. So it has 5, 3, or 1 negative real zeros. Okay, zeros. So we know it has 5 roots because it's a 5th degree. But you might be wondering why it's either 5, 3, or 1, and then on the last one it was either 2 or none. So if we go back to not that, equal to number sign negative 0. Where does it say that it's 2? You have to subtract the 2. Well, fart, it doesn't. I thought it did. I thought I saw it. Multiplicity. Okay, nearly mind. It may be in there, and I thought I read it. Anywho, so yeah, you subtract 2. On the negative real zeros, you subtract 2 if you can. Okay, let me change colors again. We'll do this one. Find all the possible rational zeros. Oh, mercy. Okay. It's kind of crazy too. So this is from the rational zero theorem. And what they do is they say, all right, A0, if I put 0 in, you get 12. Now, we all know we get negative 12, but that doesn't matter to the rational zero theorem. And then A4, so the coefficient of x to the 4th is 3. Okay, great. So then I have to do the factors. So the way that I can make 12 is 1 times 12, 2 times 6, 3 times 4. End story. And then 3 is prime, so we just have 3 and 1. Okay, so to find the all possible rational root zeros, we have to put P over Q. That looks weird. Q. And this is P, and this is Q. Let me show you what this looks like. It will kind of drive you nuts. It kind of drove me a little bit nuts. So I'm going to do 1 over 3 and 1 over 1. So I have 1 over 3, 1 over 1, which equals 1. Then I'm going to do 12 over 3, which is 4, and 12 over 1, which is 12. Okay, 2 over 3, 2 over 1, which is 2, 6 over 3, which is 2, 6 over 1, which is 6, 3 over 3, which is 1, 3 over 1, which is 3, 4 over 3, and then 4 over 1, which is 4. Okay, so now we are going to list all of our rational real roots, okay, and they are plus or minus. So I have 1/3, I have 2/3, I have 4/3. Awesome. Then I have 1. So this is 1, and then this is 1. I have 2. That's 2, and this is 2. I have 3. I have 4. I have 6 and 12. That's the answer. Disgusting. I know. Okay, last problem. Here's what I don't understand about this problem. I don't understand why they didn't give you the formula. But anyways, so this is absolutely straight from your physics book. In the Model Rocket Club, oh, I'm going to run out of time. Fart. Here, I'm just going to do it right here. I'm still going to run out of time. All right, see part 2 for this problem.